So the last time we talked about strings, and since we ran out of time, we needed to make a break. Initially we learned how strings work and how they are handled by the system. And what we want to do today is to take a deeper look on how other sorts of strings could be implemented in a more secure way than using this null terminating approach. And we will also look how generic text formatting functions like sprintf or printf work, such where you can, for example, output text to the console, and how you can convert numbers, for example, into an actual ASCII string. As we mentioned last time, it is not a completely straightforward conversion, since it requires the number to be passed and properly converted. This is not very difficult, but of course, if you just want to write some code quickly, then it adds additional steps, which one potentially might want to avoid. So being able to do it with some already existing functions, so in other words, having someone else already done that for you, is mighty convenient. So we will start with that part instantly. So as you have seen me using in the past, the printf, which stands for print format, just takes some format string, which can be just a string. It does not need to contain any placeholders. So in the simplest case, just printf test \r\n. So the escape sequences for cabbage return and new line, as we have learned the last time, which are required to advance the paper in a printer or the console output in a console to the next line. So apparently we used this already. Yeah, here we can comment this out for now, but now when we step over it, we see that it prints the test text which we have specified. And now if we want to add some sort of number, so let's say int my num1 is equals 0, and my num2 is equals 1 to 3, and maybe my num3 is equals 0x abcd. So how would we print them? There is a whole list of valid placeholders which can be used. I will copy and paste the most common ones here, so that we know what we can work with. And did it work? No, it didn't work. Why did copy didn't work? Copying across virtual machines sometimes fails. This time it worked. So as you see, every placeholder starts with a % . This is also why in the escape sequence we have this escape sequence for %. So if you would want to write a just %, we either have to use the escape sequence, or we can use %%, which also kind of escapes it. It will result in only 1% being printed, so we can quickly test this just to have it tested. As you see, despite there being 2% signs, only one is printed, so this works as expected. And then after the %, we can specify what type of variable do we have. We can print one single character, which sometimes is useful. For example, if you would have like some path for a file on a hard drive and you want to only change the drive letter, for example, that would be a useful case where it would be very handy to be able to just print one character. The next one is D for decimal or integer, basically numbers to the base 10. So let's use it, %d. And then we can specify one variable of type integer. So how variable argument functions we have learned when we used functions. We have some first some arguments, and then we have an arbitrary amount of further arguments. And as you see, those arguments here are denoted with this 3 dots. And in memory, all these arguments are aligned basically as one long list of int 64 in this case variables. So if we have a string or something that does not fit in a 64-bit slot on the stack, it would be usually passed by pointer. Right. So the next one that we have at our disposal is %e and %f, which are for floating point numbers. So we should add a floating point number here as well. My float null x, sorry, null, that's what this math 123.54456. So we can %f to print the float. Then we have %i, which again is integer, so some of them are slightly redundant. %o is for octal notation, which basically is completely unused nowadays, so we don't need to care about it. %s is for a string, which we'll test in a moment. And then we have %u, which is more or less like %i, just that it is unsigned. So if you pass a value which is unsigned, so it can use 0 up to int max, whichever that might be, then this will print it properly. If you would be using unsigned numbers, for example, as a field of flags or something, and then would want to print this as a signed number, you might end up with a negative value being printed, which technically works, is technically correct. If you convert it into its hexadecimal representation, it will be still fine, but of course for a user it might look odd if he gets, for example, an error message which is error -25 something something something. So in these cases it is recommended to use this %u. And before we go to the next ones, let's quickly run it to see that the float as well works. So as you see, it printed here this additional zeros, which it always does by default. And if we want to change that, we actually can. We can write %.toF, in which case we are telling the print function that we want to print only 2 decimal places. So now it should be only 123.45, as it is. And here obviously we'll be able to specify any amount of decimal places that you want to be printed. So this is quite useful. And the other one, %e, which should give us just the exponential notation, which might also be desirable in some cases, especially if you are doing some scientific stuff. You probably don't care so much for all the precision, and instead are pretty happy just by having the ability to simply see the magnitude of the number with which you are playing around. So %e is also quite useful. And then we have this %x, which gives us a hexadecimal notation. So we can try this out. %x, %x, comma, and let's go with num3. So here, as you will see, again, it prints now hexadecimally, and I think capital X should give us uppercase, even though it's not noted in the reference information that I copied. It says %u will give us also hexadecimal in uppercase, which I never use. Let's see if that's actually correct or if it's fake. Well, it's apparently fake, so I don't remember where I copied this from, but obviously it's wrong. It should be capital X. And of course, when you think about hexadecimal notation, you would think that, well, first of all, you would like to have 0x in 0x leading it, so you can just write 0x in the string, and then if you print it, you will just get your 0x. And then the next thing that you might want is, you might always want to have a defined amount of places. So you'd always want, if you are printing a 32-bit number, to have 8 places printed, and just basically adding leading zeros. So this can also be done quite easily. You just write %08. So first the leading character, then the amount of leading characters, and then your format specify what it actually should be. And now we will get a a really nicely formatted hexadecimal number, just as we like it. So this is quite useful. And of course, if you have, for example, writing shorts, then you just use 0x4, or if you have 64-bit numbers, then you would write 0. Well, you would need to write 016. I guess it will accept that. Let's try it out. And it seems to do it correctly, so it's smart enough that it can handle the case where there are more than 2 characters. And as you already see from here, the flexibility of this formatting function is quite high. So there are a lot of cases that would need to be taken care of if you would want to write your own printf implementation. So it's actually quite nice to be able to just use existing functions like this. So this much to that. Now we wanted to print some strings, so we can also do that. We will need a string for that, so const char asterisk my string a is equals and we can do the same with vchar by string v Unicode string, and we need to prefix it with L to note that it's Unicode, as we learned in the very last minutes of the last lecture. So again, now we just need to add %s for the normal string, and for the Unicode string this is a bit not intuitive, because you just use %S, and then you can use this print this this white version of the string. So if we run this, this will work, but we'll come in a second to the most counterintuitive version. So as you see here, it printed it fine. We can also use maybe escaped double quotation marks to make it look pretty, so that we already use some even more things in our string. See, now we have those double quotation marks, but the most unintuitive thing is that if we would have a printf version which takes a wildcard character to begin with, so it wants the format string to be a wildcard character, and now the meaning of S and capital S gets reversed. So to use the ASCII version, you need the capital S, and to use the white string version, you need the small s. And the reason why it ended up being like this is simply that a long time ago there was no Unicode. They just had ASCII strings, and when they defined print function, then they just said, okay, small s is string, and we are happy. And then they introduced wildcard, wide char functions and wide char strings, and they needed a way to also be able to print them across the different functions, so that you can use a ASCII version of a function to print a wide string and vice versa. And to do this, their simple thing was to say, okay, let them just use capital S for the wide version, and then how do they then implement the other version? And then they basically decided that small s means a string of the same type as the format string, while capital S means a string of the, let's call it opposite, but it's not really an opposite type than whatever the format string is. So this way it works. They could probably use another letter from the alphabet like %W, but it is likely that some fringe implementations use that for something else already, so they kind of did not have that liberty. So it is how it is. It is counterintuitive in a way, but once you just realize that you kind of just use the capital S for the opposite type, then it's easy to remember that that's how it should be done. Okay, so I would say this much to that. Maybe one more thing that I can show you. Here, for example, you can also specify leading characters. At least you should be able to, like, let's say 08.2 F. Then it should give us where is it here? The amount of, well, you specify 08. Okay, so it took the whole length of the string in this case and added this leading zeros. It did not define that the part before the comma must be 8. So it's again a bit unintuitive. If you would want the part before the comma to be 8, then what you would need to do is to here point, not here. So we want this to be 8. So then plus 2 and then plus 1. So it's 11. Because we need to take into account the comma, or in this case the dot. So as you see here, now we have 8 leading zeros, or rather 8 characters in our number and as many leading zeros as necessary to achieve that goal. So that's that. And what you also can do is you might want to specify that you want always the sign to be printed. I'm not sure if that works with floats, but we can try. In some formats specifies if you just add plus minus and then the thing, it will tell it that it always should have a sign specifier, and as you see it works as well. And if we then make the number here negative, it will then just print the minus. And of course, just to have it said, oops, as you see the other one where we didn't make the change here, it always prints the minus. So if a number is negative, then it will always print the, like with here, we can try with num2 as well. It will always add the minus. So you need this plus minus specifier. We didn't use num2. So let's just leave num2 or delete num2 since we're not using it and make num1. So we started make num1 containing the 1, 2, 3. So as you see, the negative is always added, but if we have the positive values, then the pluses are not shown unless you specify that you explicitly want them to be shown. So you could actually use this with D, I think, as well. If it's flexible enough, that should accept it, and as you see, it works just fine. Now it always specifies whether it's a positive or negative number. And since we are at it, we could actually take a really big integer, floating point number. Actually, yeah, let's do it like this. So we actually will need num2 to make it unsigned int. And as you might remember, the easiest way to get an unsigned int is just to write -1. But we of course can also do it the correct way. Null x ff 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 ff. But whether, I mean, this is like the definite way for an unsigned integer to define that it will have all the bits set. But of course, if you would then change this to a int64, then again this would not longer work. So it's actually probably the most elegant option to just use -1, and often the compilers will not complain about using -1 in this way. If you use any other number than -1, they will, but for -1 they really accept it, because -1 will automatically give you as many f's as you need for the size of the type that you are working with. So now we can print here %d, and here we will print %u, so that we can see the difference between actually we could also make this %i just to have used all of them, so that we see how this looks if we don't use the right Unicode, sorry, not the right unsigned version. So when we run it, then you see, what was it? Actually, it printed -1 because that's what we expect, and then of course it printed here the max unsigned int value. But if we would not use -1, but actually something that starts with 0c C000 1 2 3 1. Do we have enough? Yeah, looks like it. So for example, on the NT operating system, so basically on Windows, on any modern Windows, which is based on the NT kernel, the error codes always start with a set bit, so they start with 0C, and then you have a lot of zeros, and then you have the actual error number, and every positive value, so where the first bit is set to 0 are success code. So you can have a success code that something finished successfully, but there is some status that you still wanted to communicate. For example, if you are enumerating directory entries or any other entries, then you might want to have one return value that indicates everything was enumerated, and another return value which would then indicate it was enumerated as much as fitted into the buffer, and there is more to enumerate. So in this case, you would need positive return values. Or let's actually take a real life code, like 22 is access denied, and if you would somewhere encounter in your program such an error, then you would print it as %i. You would, instead of, well, it basically is useless in both cases. So you would get just a negative number, which looks as an error message especially scary. If you would print it as a positive number, it is also not that much of utility, since it's a very long number, despite that in its hexadecimal representation it is a very nice number. So we could here replace num3 with it, so that we have it printed nicely, and then of course here in this scenario it is printed as it should be, with leading 0c, so it's it looks really nice and does all we want it to do. Let's see what we can improve here. We can drop this, oops, because that filled in the spaces, so we got some unneeded spaces here in between. Now it looks nice, and actually we should maybe use this num2 as well here, so that we see this correctly as well. Okay, okay, so, and now there is one more thing that I would like to show you, and this is a int64 number, which needs some special treatment. So generally the typical format string formatting in Windows will assume that if you use %d, that is a 32-bit number. This has been done such that it is that you if you have old 32-bit code and you then port it to 64-bit code, the general expectation is that most of your variables which were 32-bit will probably stay 32-bit. For example, like all the error codes, some of the enums, many other things. Basically, the only thing that must change is pointers. So all pointers in 64-bit are automatically 64-bit. There is no way around it. And what would be useful to have in 64-bit would be, for example, file pointers. So things which reasonably can be more than 4 gigabyte. If you have ever worked with some very old computers, you might notice that they might have a limitation that if you stick in a very large USB stick, it will only detect it as a 2 gigabyte device, and this is because it would then be limited to count the size using a 32-bit integer. So if you have some old 32-bit code which uses file pointers, then it would be good to upgrade this to explicitly use a 64-bit value. But for any other, or at least for most other reasonable applications of a integer, a 32-bit integer is plenty large, so there is no need to do that explicitly. So let's write some really big number, null x 1 2 3 4 5 6 7 8 9 0 a b c d e f. That should be plenty big. And now if you try to print it, let's use a new line for that. Printf, just %d or %i, doesn't matter, with our number. It will usually not work. So the expectation is, as you see, that it just truncated it to the last. It just printed pretty much just the second half of it. Yeah, that's where the second half starts. So if we would have removed all of this, we can quickly remember the value. It's 18.6 something something. So if we run it again, we just get the same 18.6 something something. So as you see, it's exactly what's happening. It is truncating it. So the question is, how can we fix this? And this will of course also happen with %d. It should fail in the same spectacular, or maybe not spectacular, way. And the way to fix this is to add additional parameters like ll, which stands in for long, and then if you print it, then it should give you the whole number. Obviously the number now is in base 10, while we wrote it down in base 16, so it's not quite what we wanted, but we can use, I think $p should be supported to use to write this pretty much as a pointer. So as you see, so generally $p is defined as a pointer. So if you are on a 32-bit system, $p will, or rather if you are running a 32-bit application, $p will give you only 32 bits. So you should not use this $p to print things that might, even on a 32-bit system software, be 64-bit, like the aforementioned file pointers, file sizes, stuff like that. And the way, just to remind you how a 32-bit system handles 64-bit numbers, is that it pretty much does not. The software has to do it by hand. You simply have a variable which contains two 32-bit integers, and then if you do any operation with it, the operation is broken down into multiple operations where every single operation is 32-bit or less. So this is of course notably slower than natively handling a 64-bit number, but since usually you need such numbers in a 32-bit software only when working with some file offsets or file sizes, then it is used rarely enough that it does not really constitute a performance limitation in real life. So the next question will of course be how to print it properly, not using %p. Actually, don't remember what was the trick. I think it's just LLX. Let's quickly see if that's correct. Yep. So you just can prefix LL with whatever existing thing you have, and then it will automatically print it and be able to use all the bits in your number. So we will add here this %p as well, so that we just have all the options. %p. %p is quite useful because it's easy to remember, and I think it already printed it in capital letters, so it really gives you what you expect from a pointer representation. The only thing missing is that you are missing the 0x at the beginning, which you are always missing. You just need to add it manually in the string if you want it. And the reason is because 0x is not necessarily like a universal. It's something that is very common, but you can also use was it either the h is either as a prefix or as a suffix. I don't actually remember what's the standard, but you could have such a notation as well. And also there are some scenarios where you don't even want to provide a specification, whether it's a base 10 or base 16 number. In such situations, the compiler just looks whether you are using A to F or whether they are just numbers. So then you only, so it's smart enough that you only need to specify that it is base 10 if you, or rather that it is supposed to be base 16 if you haven't used a to F character inside the number. So there are some parsers which try to save you from having to type too much, but in reality it just makes things more confusing. So I would recommend not using such scenarios, and if you ever encounter any sort of parser or similar thing which tells you that it actually can handle intelligently detecting which sort of base you use, that you still explicitly provide a base specification, because otherwise that can end up in a very hard to find issue. Okay, do we have anything else about strings to say? I think we covered everything that is important at the start. We can try out other versions of printf. So we can create a string. Let's say a long string, my string buffer. Let's go it like this. Let's give it a kilobyte in size. And now let's say we don't want to print our text to the console, but instead we want to print our text to another string. So if you are, for example, printing to file, there actually would be a special function for that, fprintf, which allows you to print to a file object, but this is something we'll take a look at a bit later. So what you would be using if you really just want string formatting, you are using printf, and I guess underscore s, otherwise it will complain, as we remembered from last time, that it's not the safe version. Although, is that the safe version? No, yeah, it is the safe version. So and it's the do we want the vs printf to actually have this? Some of the that's svprintf, that's the right so the notation is a bit not always intuitive. So for example, printf is just prefixed with white, but like with string is string white printf underscore secure. And of course, when printing the console, you don't need secure because you don't have anything to overflow. But if you are printing to a string, then you need to specify. Was it in bytes or was that in counts? Let's quickly review. Buffer count. If it's buffer count, then it should be in character count. There is this array size preprocessor definition, with some where at some point okay, they made it much more complicated than it needed to be. Let's go on. Define array size x. And the simplest way such an array size macro can work is, obviously it only works with arrays which are defined in the at the same place. You cannot use like a pointer on the array to get this out. I think I demonstrated that when we talked about pointers, but here I just wanted to show it again. So we take size of our variable, so size of x, and then we divide it by size of x0, and this gives us automatically the count of elements in the array. So this is quite a neat shortcut, and as you have seen, there is also a array size in all capital letters defined as part of the standard template, standard include headers, which you can use. And usually I would of course recommend using the standard things, but here I wanted to just define it so that you see how such things can be implemented if you are trying to do it easily. Because like nowadays all the modern libraries, they're usually mostly overcomplicated, such that while they of course do what they are supposed to do and do that very well, it's difficult to learn something from them because they are using so much more esoteric functions in the language that it's not straightforward to understand what they are sometimes trying to achieve. So as said, let's continue here. So we have our string. We told our safe or secure svprintf function how many characters it is allowed to write, and then we can just copy the whole rest here and paste it, and then we can use then just for fancies printf %capital S, oops, comma, and then we print our string. As mentioned, with a file you could use the fprintf or probably fvprintf to write it to a file, but then you would need to have opened the file using the standardized fopen and so on. So what you then get is usually not a real file handler, but a handler in the sense that it's something internal that the library, the IO library is using. Although that is not guaranteed, it can also give you the real file handler. It will really depend on the internal implementation. And all the standard Windows API functions, they want a real file handler, as you can get with NT-create file or NT-open file, or just without NT, or so just open file. The NT prefix tells that it's a function usually located in the NTDLL, and it's a bit harder to use since it actually does not understand drive letters, or at least not in the native notation. You can use a backslash question mark backslash and then use a drive letter to make it work. But a normal path, as you would just copy and paste from Explorer, which just starts from a drive letter, you couldn't use. So therefore you have the normal open file function, which is implemented in the kernel 32 DLL, which then does the conversion to the NT path notation and then feeds the properly NT formatted path to the NT open or NT file create function. And just on a side note, while there are functions called file open and others called file create, usually it is not such that the creates a new file and opens an existing file, but rather the create file is meant like create a file object. So a file object in the kernel, not a file on disk. So you can use a create file call to open an existing file, or you can use a create file call to create a new file, and or you can even specify that if a file is found, whether it should be kept or it should be truncated to 0. So there is quite a lot of flexibility available with regard to opening files, and the NT-open file call could also be used, if I recall correctly, with the right parameters to create an actual file on disk. So in a way, it's kind of redundant sometimes, and it's to some extent for historical reasons why the things have been made this way. I guess the most useful case where you cannot create a file object is if you are, for example, opening a pipe. Then you should just use open file, because then there is no actual file object, but you are using pipe, so internally it is represented in the kernel in a different way. But anyhow, let's quickly run this code so we see. In the end, we have printed it again. Yes, we forgot here to print some \n. We can of course here add some more, and we forgot the \r, so that we have one clear line between those two attempts. Is that what I wanted to say is that if you would write a file using the Windows native API, like just the NT-write file, or just write file from kernel 32, then you would need your formatted text to already be in a buffer. And this you can do with this sprintf. Or another use case where you would be using this sprintf is if you want to send something over the network, or if you want to show a message to the user where you cannot use printf. So do we include Windows H? Yes, we did. So if we have Windows H include, we can actually very simply show a message box. Show message. So message box, and this is available as A for ASCII string and V for white char, white char string, and then we just specify, okay, high instance, let's say null, window null, text. Then we take our text, and then some title, then we can specify a style. MB, okay. No, we don't want shell message box, we just want normal, just want the normal message box fee. Shell message box fee is, yeah, okay, then we have one less argument, text, title, and MB, okay. And as you see here on the argument list for the message box W, you don't have the ability to specify additional arguments. So it's not, the text must be a text, it must not be a format string. So that's why you need to pre-format your message for showing it. And as you see, voila, it just shows you the message. So on Windows, it's, as the name suggests, maybe very easy to show windows. Although as soon as you want to have a window that is not a standard system dialog, it gets slightly more complicated. We will not be taking a look on showing window objects and those things in part 1 of the lecture. This is something for part 2 in the next semester. So if you are interested in creating any sort of graphical interfaces for your users, then you will need to attend the part 2 as well. In part 1 we only take a look on all the low-level things and the basics, so that we have a good understanding of how C and C++ work, so that we can then build on top of that. Right, so we had here our printf, and last thing we should take a look at when thinking of strings is if we want a string to be safe intrinsically and not have to always pass multiple arguments around. So you can imagine that if you would allocate the string dynamically with heap_alloc or malloc, then we would need to have a second variable which would hold the length. So we could not get the length using array size, since it's dynamically allocated memory. It's nothing that can be estimated during compile time, only during runtime, even if it would be predictable. In practical use cases, you might have really a dynamic length. So if you would have a file path which the user can specify and you want to print a message which contains the file path, then you would allocate enough characters for your message and then write plus length of file path, so that you know that the resulting string would be always of the right size. So this is something that would necessitate you to always carry around two variables, one for the pointer and one for the length. So what the simplest, most intuitive way to solve this issue would be is to just create a struct. Struct my string. Let's call it my string. And the way we do it here, we add a prefix my string, comma. You might notice here that I am defining the struct slightly different than we did it before. So before we just defined a struct like this, and this is perfectly fine. We just specify the name and that's it. But the very old style C way of defining things is that if you want to use the struct as a type later, you need to write typedef. Then you can write your struct with the name, and then you can write the actual name of the type you want the struct to be used at, and then you can also specify a next type, the pointer type. So p my string would be just a pointer to my string. So if you would have a pointer variable, you don't need to write my string asterisk. You just write p my string, and it is apparently supposed to be more elegant. I don't necessarily think so. It just complicates things in a way, and it doesn't save you on typing, because you either write p or you write the asterisk. So I mean, you could probably, I guess, cut off a letter if you really want to, but this would again be against the standards, because the convention is that you just prefix p for a pointer type and not change the actual type name, so that you always know to what the type name refers. And of course now let's take a look on the insides. So you would have one unsigned short that contains the length, and ideally, if we don't want to use this null terminator, the length would really represent the length of the data of the actual valid string. So in this case here, as you might have noticed, we allocated the whole kilobyte, but we just used maybe 100 bytes at most from the beginning. So here we would have two variables, length and max length. And while length would be the length of the string that actually is contained in our buffer, maximum length would be the size of the buffer. So when we create an empty string, length is 0 and max length is, in this case, it would be 1 kilobyte. And then of course we need the string itself. So buffer, and this how such a improved better string structure would look like. In fact, this is quite similar, or actually identical to how the Windows NT kernel, so the part that usually people don't interact with directly, handles strings. So all the NTDLL APIs expect not null terminated strings, but strings in this format. They're just called Unicode string. I'm just not sure if this it's not defined here, so we need to hash include oops, internal h. So as you see, this string is not even part of the Unicode string used. It's not even part of the standard Windows header. The reason simply is that the standard Windows header was intended to be used with even the very old Windows versions like Windows 98, 95, which was not based on the NT kernel. So Microsoft had like two completely different Windowses in parallel, which coexisted for 5, no more, 7 years or so, since 1995 until the Windows Millennium, so 2000, but it kind of then it was released, so it was supported for a couple years more, so it was and sold. So at least for 7 years, there were two completely different Windowses on the market, which were completely within reason at least compatible. So as long as the developers only use the standard Windows header, a application compiled for either of those Windowses would run on the other. And this WinTernal, like Windows internals, is a special header which contains all the NT-specific stuff that was not present in the old DOS-based Windows 95, 98, and so on. And then there also is, of course, a ASCII. Was it ASCII string? One I think it was one I. I don't remember what the other one was called. ANSI. ANSI, not ASCII. ANSI string is the so the Unicode is the VCHAR version. So as you see here, PVCHAR, which then goes to our type def of VCHAR, which is defined again somewhere. So as you see, you can have quite a lot of complication. But the way this is done is to have like the most platform independent. So if you would have a platform where your VCHAR would have a different length, for the Windows kernel you always want the unsigned short length of your VCHAR. So this is not just for shits and giggles, how one would say that, but it really has a purpose. Why some things, especially in universal or at least most universal libraries, are sometimes written in a rather inconvenient and very convoluted way. And now if you look for the string, actually it's just a placeholder for string, which then has just pchar, which just goes to char, which again is just defined as char. So we have multiple layers of definition. And an important thing to remember is that all this definition stuff, preprocessor stuff, it has zero impact on runtime. It just makes your compilation take longer, but the resulting code is identical whether you would write everything in one place or do as much redirection and generalization as you want. So this is fine to do it this way. And such a string structure you might want to create your own for some applications. Of course, in reality, you probably will not write any plain C code. You will most certainly in future, aside of this lecture, write C++ code. And for C++, you have the standard template library, which contains a very advanced string class. Since we are at strings, even though we have not yet learned what a class is, I just wanted this to be mentioned, that you know that in future, if you will want to use strings, you will be just using the std string, which does not have a. We would need to include another include for that hash include string h, but we'll comment this out since it's yet outside of the scope. String and base string. Base string is again wide string. Okay, and I think this is the final extent of our string sample. So I will upload this to the Moodle after the lecture. Now let's create a new project, and as I promised, the new project will give us some opportunity to give you some homework. So let's create it, create new project, and we will call it simple list. And the simple list will be an own list class. So as you have already seen, you can easily use arrays and work with them, but they are, at least the simple ones, are limited in as far that they only have a certain size. You cannot resize them easily. You could just create a new one, copy everything over, and then be happy with the result. But in many applications where you are, for example, adding elements to a list, you would want to avoid to have to replicate the whole list multiple times over. and in specialist scenarios you would want to have a granular memory allocation, so you would want every element in your list to be its own object in memory and not part of one larger memory block, such that, for example, you could remove an element from the middle somewhere and then not have to like consolidate the list by copying half of it one position to the left, or two positions, or however many elements you have removed. So obviously with an array you can do all those things, but then you just always need to shuffle the elements in the array around, so this is not super convenient. So what usually people do if in such scenarios is they are using some sort of list structure. Of course, once using STL, these things get kind of much more simple because there are already working STL list and so on container types, but you cannot use STL everywhere, at least not easily. One example would be, for example, if you would be writing a driver for a Windows kernel, then there you don't have STL support. There are ways how you can introduce enough of C++ of the C++ runtime to a driver that you could use STL, but then it still wouldn't be recommended because STL was simply made for a user mode, and you would not want something that is prone to throwing exceptions to run in kernel, since the kernel does not have any exception support, which again for your driver you could to some extent hack in. But the general recommendation would in this scenario be to just write your own container type, which by the way is something that we will be also doing in much more detail later. But ideally, in such a simple scenario like a driver, especially if you want it to be as performant as possible, you would not even write C++ code, you would just write plain C code. And since we are learning low-level C, we will start with a very simple variant of a list, which is called a linked list. So the way this works is we first start with some list entry, so struct my list entry, let's call it, and the thing then will need to have a pointer on the next element in the list, so my list entry p next, and then it can contain some data. Let's say int data int. And as you might remember from earlier, we can put one structure in another structure in another structure, and then still be able to access the elements easily. So usually the recommendation would be that instead of creating an own list implementation for every type that you want to store inside your list, that what you do instead is that you would just have a prototype list and then just create some sort of struct my list entry with data, which then as first element would just contain your list entry, and then you would have here your int data 1, data 2, data 3, data 4. And then if you write all your functions such that they will work with this type, you can either pass this entry directly, or you could also just cast your original variable onto the type that your special custom list functions natively take. Okay, and the way that and there are basically two ways how you can implement your whole list. You can have like the, let's say, the super easy approach where you just make a pointer to the first entry and then say, okay, that's my list head, and then I'm happy with that. And there are implementations which are really as simple as that, but since we have high ambitions, we will create another structure which will actually represent the head of our list, or rather all the information that we might want to associate with the list. So we will call it just my list, and the thing will contain a list entry, then okay, head. We will create also another entry tail, which we will not use yet. And since we would probably want to know how many elements are in our list, we'll make a size underscore tu count, which will trace the count of elements in the list. Okay, and so now in our main function, let's create a list. I'm thinking about the naming scheme. I would actually prefer maybe to use this time the camel case notation. That is prettier. With data. And now it doesn't cost us much to change it. Later it will be more typing. Yeah, because now I can just write my list and list, because like a small list is the name of the list in STL, so I would advise to try to not use variable names that might be a type in STL, even though the STL is isolated by an own namespace, so it should be fine. It's just better practice to not do that. Okay, now we will need a function to add something to our list. So void add to my list add entry, or just my list add. That is good enough. This will take a pointer to our list per list, and it will take a pointer of type my list entry then yeah, p entry. We could, by at this convenient case here, also use this type def struct, but then we need to underscore that, then give it the name. Or actually, what we also can do is we can keep the name here and then just make here p entry asterisk. So we could do this, and then we could use per. Oh, it was also wrong here. But I think this just makes things more confusing. So let's keep the code more self-explanatory and keep it like this way. So here it should be an asterisk, since we don't want to use reference, just the actual pointer. So here now, if we are creating our data, so we will need to have some sort of my data per entry. This is for the pointer again. This equals, we will need to cast malloc size of type name. Asterisk is missing. Oops. Yeah. Okay, so we have created our entry. Then we can add it. So add list reference list, since we want the pointer, and then we add the entry. In principle, we could expect this to be able to return an error value, but we don't want it. And now, as mentioned, there are two ways. We can either have entry, or we could just cast this, which I prefer. This will work just as fine, because all the internal logic, it doesn't care for the additional data attached to our list entry. Oops, that's a typo. There should be an entry, not an entry. That will be a lot of typos. Okay, typos fixed. My list entry with data. Yeah. So now when we are entering the element to our list, we have to well, first of all, the simple case, the first element we just set the head pointer. So if head, if list head is equals null. Oh, and we forgot to initialize the list. This is a bug which we should not introduce. So let's use one of the standard functions. So we can clear the list using memset. List, reference list, comma 0, comma size of list. So memset is just a function provided by pretty much any C++ framework that allows you to just set a memory region. You point a pointer, you give a value that you want to be there, and then you give the size to 0. So memset works here quite nice. Now with very modern C, you could do this in a different way. You could just write initialization values here and then have the initialization will be done automatically, but this is something for C++. It doesn't work in just C. So actually what we might also want to do is we could rename this file to be as simple as C and not C++. Oops. Rename. This will ensure that we will not be able to use any C++ features, and as you see already here it is complaining. So type def stock underscore mylist comma stern p mylist. So okay, size, isn't size t defined? Size t should be defined. It's not Windows H. Size t will be defined, but it's only defined in Windows H. And again here with mylist, it also complains that you cannot use the struct as type in just plain C. So in plain C, we don't have any choice but to do this. I mean, we could do it just like this. We don't need to define a pointer type for ourselves, but since we are at it, why not? And here, of course, again the same situation. Oh, that is how I wanted to make this look nice, and then I introduce another typo. Yeah, that looks nice. Okay, so now it's not complaining, and also in C, sometimes casting is much more liberal, so you can just do things like this, and it doesn't complain. You can just cast a pointer of one type on a pointer of a completely other type, and C will not tell you that that might be a really bad idea, at least without knowing what we are doing. In this case, we know what we are doing, so it's fine. But I mean, it's more convenient this way, obviously. But as said, let's return to our code here. So the simplest case, head is null. We have memsetted it, so we know that for the first insertion it will be null. So here already we can set up the... Actually, we could just put it in a loop. For int e is like null, e less than 3, e plus plus, and we can also yeah, doesn't matter, that's fine. So we will add, oops, the autocomplete is still on. Right, so here we can also data1 is like I, so that we know which entry it is. Or I plus 1, because we want that to start at 1. Okay, so we did. So we will add the same element 3 times, or rather not the same element, we will create a similar element 3 times and then add it. Also adding a space here, sorry, a new line here looks better. So in the simplest case, we just write list head is equals entry, and we are done. Oh, and I forgot here to memset the entry as well. Forgetting to memset things is a very common mistake. And this is the reason why in modern C++ you are supposed to, as we'll see once we take a look on C++, to define the initial values directly when defining your variables. But in normal plain C that was not the case. So we always need to memset things. In principle, we could also not memset them, but only set the variables that we know needs to be null. But since memset is usually implemented in a highly optimized way and will not need many CPU operations, unless we are memsetting something that is really big, like a string buffer or something, then just memsetting the whole thing is even usually more efficient than having to manually assign 0 to a bunch of individual variables, which might not be properly memory aligned, and so on and so on. So just memsetting everything you have allocated is fine. And you might also remember heap alloc had a flag where you can tell it that you want already memory which has been zeroed. So that is something that you could use and then save on a line of code or 2. But rather than 1 to be exact, since it's just a memset line that you would save. And then of course, now if we can keep thinking about our list, another thing we need to do is we need to increment the counter so that we know that something is there. And now the next case, so how does the insert works if we already have something? And As you may have already deduced from how our entry looks, the only thing where we can put the next entry would be to this next entry in our existing entry. So we could either find out what is the last element in our list, and as you can see, since we only have a pointer to head, we don't really have a means to estimate how many elements are there. That's why we just have a dedicated variable. We could have used this another variable to always track the position of the last entry, but assuming it is a singly linked list, so we only have pointers next and we don't have a pointer preview. So a singly linked list is a list with elements linked to each other in one direction, and a doubly linked list is a list where you have elements and an element is not just pointing on the next element, but it's also pointing on the previous element. But in this case we don't want this, we will comment it out. So what do we do here? There are two approaches. One would be the simple one. We just cache the pointer that is already inside. We can call it p old or p old head or something. Then we copy head to it. Then we just do that. And then we just need to remember that our new head next must be pointing to what was the previous head. That's the simplest approach. It gives you the fastest insert performance, and it's pretty much the only reasonable way to do it with a singly linked list. So having like so basically the add function always is actually a prepend function. So it adds to the beginning of the list, which is somewhat counterintuitive. You really would expect if you add things to the list, you would add it at the bottom. But with a singly linked list, you cannot do it. You can only do it with a doubly linked list. So that will be the next thing to implement for this, to make it doubly linked. But that will be the first homework. But before we write the homework down, let's quickly see if this thing works fine. Okay, it does not. It says right. It does not. It doesn't find itself. Okay, then we just can go with a void pointer here. That would be working just fine. Should be working just fine. List entry next. No, it will not be working just fine because it doesn't know what this is. We need to tell it that it will be a struct of this type, then it should be able to accept it. Yep. Okay. So as you see, we have now inserted the three elements. We didn't do much else, so let's put a breakpoint here. And the nice thing about the Visual Studio is that we can use the locals view to inspect our list. So we have a count of 3, which is correct. We have the head. What we are missing here is it is not showing us the data because it only knows from the source code that the entries are of type myListEntry, and it doesn't know that there can be data attached to it. So we can only see how this works. We could take one of the pointers, copy value, clean it up a bit, and I hope that it will be smart enough to do that. Actually, don't remember whether that worked, but yeah, it is working. So as you see here, we can cast to the type inside our ImNet window, just providing a pointer, and this thing is smart enough to then print for us the entire content of our structure. So here in this case we took the head, so here we see the last one to be inserted is really at the beginning, so the insertion direction is reversed, and here we can then get a p-head. First called entry, was it capital? Entry dot my list entry has no member entry. Then it should accept head. Sorry, it's called p-next. I was distracted. And then another p oops, p next. So we can in this way step through our list quite conveniently. Of course, if we would only be using this list once, we could just keep our data inside our entry. Then the locals view would be a bit more helpful. But since we want our list to be generic and to be really generic, actually you should keep everything that's specific in one place and then our specification further down. So the next thing to implement will be some ability to iterate through the list. So we want to be able to do something, for example, print to the screen the value of each data1 variable. So how do we do that? Well, one option, of course, is to just use a for loop. So for entry with data, then p head is equals list. We just grab the head from it. Then we check whether that is not null, because it could be. So if this is not null, then we can execute the body. And once we are done, we just write head is equals head next, entry next. Should make entry capital as well. That looks better. Next, and then inside here we can refer to head data1 printf %d\n, or let's say entry and number %d, comma p head. And now if when we run it, it will print 3 to 1. We have a typo. Let's see, and we want build only. Need to return a value. Did I overwrote this? Now it's complaining about printf. Printf, that should be always included. Let's add stdio explicitly. Okay, so for some reason when we had only Windows included, we had the definition of printf, but we were missing the library that contains it to be included somehow into our code. So we have just to add stdio, and then everything works out fine. Alright, we wanted to see the results. So as you see, entry number 3 to 1. It is properly printing itself all its way through our element. So as you see, you basically only need a add function, and that's already it. What you then also probably would like is an ability to remove an element from the list. So to do this, we would already need a doubly linked list, at least for this to be trivial, because if we only pass it the entry does not know what is pointing onto it. It only knows what is the next thing. So since we don't have a method to easily create a doubly linked list here, I mean, we don't have a method. The thing is, that should be the homework, so I cannot do it for you, so you will need to do it yourself. So we need some other method how we could remove elements from the list without having it being a doubly linked list. And one approach would be that you would need a function. I mean, you would always need a function, but in this case the function would need to get a pointer to the list itself. My list there, or remove, and it will need to go through the whole list to find the entry and remember the previous pointer that pointed on that entry. So if this would be a doubly linked list, the remove function could be made much more efficient. So this is something that we will want to do later, but for now we will want to remove from list the second entry. So let's take the list punct head next. So obviously you would probably have a loop that is a bit smart and then finds an element and then removes it, maybe, which we could do next. We could add a find function, but in this case, since we know that there's 3 elements, we can just want the second one to be gone, so that we expect the function here further down to just print 3, 1, nothing else. So let's now take a look on our remove function. So let's start with a pointer to a element, and we'll use a pointer on a pointer. So actually copy a few things. So pointer on a pointer on a reference on this. Okay, now if, not if, that will need to be a loop. For one thing we can check obviously for is whether this is not null, because if this would be null, then we cannot do anything, then we should break. And now inside we will check, so if asterisk old head is equals entry, so we are checking whether our old head is the entry that we want to be rid of. And if this is the case, then we can write a new head. So we can copy some code from here, because we are lazy, call it a new head, then take entry next, because we need, I mean, this will not be a head, that I should not have called this a head, because the head, it's only head for the I mean, here it's fine, but here it's not, because it's only head at the first go through. So let's call it old next, and like this is fair enough to call it old next. Then we will call it new next is entry next. Okay, and now we can take our old next and just assign to it our new next. I mean, we don't need that in the intermediate variable, but it is good practice to keep. Actually, it doesn't matter. It's pretty enough. It's pretty enough. Let's do it like this. That should work fine. So let's see if it works. If we would be more complex with our code, and we would want, no, it fails. We didn't find it. If we would want to be more complex with our code and delete the element from memory, then we would want to make this code more complex, but we don't want. We forgot to add one thing here, namely that we want to advance to the next entry. And this should also be called head. So p old next, so asterisk, so just the p old next is equals asterisk, one asterisk, reference asterisk p old next. We need to put this in brackets. Reference asterisk, that's right. Okay, now it should work. Let's run it. And voila, it only printed 3 and 1. And the thing is that at this point we have a memory leak, because we have not removed this element. So let's cache it in a variable. Then let it be removed. And then we can free it. And one more thing we should do is we could add here a boolean and return true if we found and actually removed the element. Boolean only is valid in C++, but there is a preprocessor Markov for Boolean and so on capitalized. We just evaluate to 1 and 0 and Boolean to integer, which we can use instead in plain C. False. So ideally you would check whether this worked. So if we removed it, then we can free it. And obviously in this case we know it will succeed because we took the value from here, but we could have taken the value from somewhere else, and then we might want to be careful with deleting it prematurely. So as you see, it is quite easy. So basically what is happening is we can maybe write it, draw it to make the concept of such a list more illustrative. So we have somewhere a management structure that shows you on one entry, and this entry contains some data, and then it contains a pointer. Actually, there are errors. On the next entry, which contains an entry on the next entry, and the last thing is just pointing to null. And now if we want to remove one element, then what we do is we make this point. That's the wrong feature. This one maybe. Yeah, that looks like this will do it nicely. So what we instead want to do is we just kill the element and then make this point onto the next. As simple as that. And with a doubly linked list, of course, we would just have errors going both ways. And once the element has been unlinked from the list, then we are free to delete it from memory. Or we could reuse it for something else, but that would not usually be a necessary approach. So, right. So, are there any questions to lists? Is that all clear enough? Okay. If there are no questions, then let's continue. As mentioned, these two functions are the absolute basics that anyone would need to interact with lists. So now let's write down the homework for the next for the next lecture. What's the date? 25/04/2024. Okay, so and let's add some line breaks to make it more readable. So we'll change this to prepend. Let's go like this. Okay. And okay, good. So this is this, and we have our add. Actually, I could just rename it. That's my list rename and implement. Yeah, that's. I think this is more reasonable. That will make things more straightforward. I mean, we could add a append function that would just go through the whole list in an efficient way. I'll write it and implement a new mylist append, and we will now quickly write an own list append, which will do it in an efficient way. Just so we have it. So just that we just have the functionality, because this appending is nicer than prepending. So I mean, nicer. It's more intuitive with regard to what one would expect. Obviously, the initial portion will be the same, since if there is only one element, we just replace the head. But here now we need to find the tail. So we can steal some code from here. Let's see to which extent we can reuse it. So this needs to be like that. We want this, this should be of course a simple thing, and we would want this to be a pointer on a pointer, and we'll call it tail. It starts with a reference on this head. We check whether it's not null. I mean, we know that the first one won't be null, but just for completeness we keep this way. Although when I think about it, we could, in principle, leave it as is, and then we don't even need the first case. Let's first implement this, and then we'll see how we can simplify the code. So this will want to be placed before. Yeah, we really will not even need that code, since the thing here will just bail out. So if we are in case 1, this just is not true, and then we just exit with this set. The other case is, of course, when this is true, and then we actually want to do nothing, so we just put a empty semicolon, and our for loop will not do anything. And then we want, of course, our p-tail to be what was it? Reference, dereference, p-tail slash next. Voila. We can of course put this comma here directly. It gives us like an infinite loop which only does checking and incrementing. And the way this code here works is it will loop until we find the last entry where tail is null, and then we can just set tail is equals, so asterisk tail is equals p entry, and we're already done. So yeah, almost. We need to increment the count, obviously. Let's write it like this. Now in modern C++, you, at least in depending on your configuration, you could have this standing here and then refer tail outside of the for, but this is kind of counterintuitive since this is already in the scope of the for, and some compilers don't like it, so we will keep it the right way and have this initialization of our loop variable just before the loop, so that we can definitely access it in any scenario. And now we could rerun the code. So now basically we expect the thing to do the same, just it will print 1 2, no 1 3 instead of 3 1, and voila, 1 3. As you see, it works. And really, while this code doesn't look much bigger or much scarier than this code is highly inefficient, because if you have like 100 elements to add the 100th and one element, you need 100 operations, and if you have 1,000 elements, it will just get slower and slower and slower and slower. We could actually test this here. So we have here our loop. Let's define a variable around start equals get tick count. Get tick count is a Windows specific function. It's not available on Linux. There will be other functions which will do a similar thing, although maybe we should follow the recommendation and use the 64-bit version. Let's say keyword, I think. Okay, well, it's a long, but a long and a don't they have keyword? Maybe keyword is not defined. Keyword is not defined. I don't know. Okay, is this defined? I don't like this long way of writing things. It sounds redundant. ulong64, as you see, is defined as just unsigned in 64, and long is defined as the exact same thing. So it doesn't matter which one we use, even though the return argument here is different. As long as it evaluates the very same real type, it's fine. So we'll keep it like this. Right, and what does the get tick count do? Get tick count gives you the amount of milliseconds, usually in an increment of 10 milliseconds, or rather, not in an increment. It gives the number that you get is in milliseconds, but if you just call the function multiple times, it will give you the same number until 10 milliseconds pass, and then it will give you a number bigger by 10 milliseconds. So the internal counter, which is counting, has a sufficiently bad resolution that you don't get a 1 millisecond resolution. There is some API that you could call to switch to a high performance counter, which then should give you really 1 millisecond resolution, but for here we don't care. We will just make this value here so big that it will definitely need more than a millisecond or more than a few milliseconds to complete. So we should be fine. And then we now just can copy actually the whole line and just call the other one end. And then we can print f %s, no, %d, ms, no, we need LLD. Oh, and I forgot the quotation marks. So operation took %LLD milliseconds, comma, end minus start. And of course we could just have this directly here, but let's keep it in this more elegant way, and let's see if 100,000 operations is actually enough to take any time. Okay, apparently it is. It might be too much. It takes time and takes time and takes time and takes even more time. So as you see, it kind of already takes forever. If we put a breakpoint here, we manage to hex is not helpful. To just 80,000. We are close to the end. The end is nigh, or how those end time prophets are usually saying those with their English American accent. And voila, it finished at some point. So actually this is too much. Let's just go with 10,000 and put a breakpoint, and maybe then double the whole thing. The thing, when we double it, it will complain that we have already defined use start. So what we can do, I mean, we could just reuse the existing variable, or we put it in the code block. Then use start is in the scope of that block, and then we can just repeat it. And here we will first let's do the let's start with append as we did, and then let's go with prepend for the fast. So prepend took, and here took, and then we will just run it, put a breakpoint here, and then we'll see. Okay, that was much faster, and we forgot the backslashes. But as you have already seen, for one of them it said it took 0 milliseconds, which is not realistic, but obviously it's it shows you already the time difference. So the first operation, where it each time needed to iterate through the list, it took 110 milliseconds, while in the next one it took 0. So it obviously it wasn't really 0, but it was so fast that this low performance counter didn't manage to register the next 10 milliseconds having passed. Now if we go back to our just making it 10 times longer, if the problem would be linear, or of an order of 1, then the whole thing now, since we made the problem 10 times bigger, it should take 10 times longer, meaning it would take 1 second. But as we have seen, it took much longer, and the reason is because the problem is basically exponential. So the complexity, since each time we have to go through the whole list over and over and over and over, it is more or less quadratic. So now it will take like 10-ish seconds to complete, even though we have the time required increases by 2 orders of magnitude. Well, almost more than 2 orders of magnitude, 2 orders and a factor of 2, while the problem itself was only increased by 1 order of magnitude. And as you actually see, the other case still took 0 milliseconds. So for the other case, we could actually give it I don't know, 1,000,000 insertions with that. No, I want to break. I don't want to waste time. Let's remove the 0 here so that the top case is fast. The bottom case, right? So the bottom case needed like half the time to insert 1,000,000 elements, while the top case needed needed almost twice as time for only 10,000 entries. So as you see, this line here is highly inefficient. So if you want to add things to the back, it's really good to use a doubly linked list, because then, as said, it is fast because it has already this tail pointer cached always here in our head structure. In principle, we could like cheat and make this a singly linked list, but one where tail points to the back of your list. So if you know that you want to insert to both ends, but you always want to traverse the list only one way, then you could in fact create a singly linked list which has a tail pointer, and then you can work on it from both ends. But then what you cannot do is you cannot go from the tail and go upwards. And since we want to be able to iterate the list in both directions, we want this to be enhanced by you to be a fully doubly linked list, which can then be really traversed in both directions. So we have here our, let's leave this at 10,000, and then we will just comment it out since we don't need it now. We will just reintroduce this code block with maybe 10 entries, let's say, so that there are at least some. Right, and obviously with 10 entries it's super fast, so if we just run it, we're already done. We are faster done than we can blink. And we will now take a look on what other nice things we can do with such a list. So one obvious thing would be that we might want to search in the list, but that actually sounds like a good homework as well. So what we could do is we could make it more convenient to iterate through the list. So you always need to write this much code if you want to go through the list, which might not be the most convenient way. So what we can do is we can add a function here, void my list iterate my list, iterate my list, or my list iterate. My list iterate sounds better. It will take a list, and as you might remember from our lecture about functions, we can not only use functions in C++, but we can also have a variable which contains a pointer to a function. So we could basically write a code that expects a function of a given prototype, but at the moment when the code is written, we don't need to define which function this is. So we can later in some other place of the code, or even in another library, define that function and then pass it along as a function pointer, and then the other code, which only cares for the address of the function and its prototype, will be able to properly interact with this function. And we can use this thing here to implement this iteration. So we will need to write a function pointer as argument. And since function pointers are kind of confusing, they have a really weird notation, as you might remember, we'll just type def as the right function pointer so that it's easy. So we start with type def, then we start with the function pointer definition. So it's in brackets asterisk then the name. Let's call it t for type def, t iteration func, or maybe t my list. Let's call it just my list function, my enum function. Let's stick with this name, and then we write the argument list for our function. So this will just want to receive a entry as a pointer and nothing else, and then we can use our tmylist function. Let's call it function, and then we just steal some code that we've already written, and then we can just list is now a plist, but it's only very simple, and we should not call it head, we should call it p current. Could also call it entry, and then just go to entry. That would be also fine. Although here we will want to use the generic version, so here this will be changed like that. P entry, P current. Yeah, current is fine. Then we can directly call our function and pass current as an argument, as an argument to it. And now when we want to iterate through our list, we can do it in a slightly more convenient way. Iterate per list, zack, comma. That's a good question. Whether actually plain C will accept that. It might not. It might not. So if this would be a CPP file, then this code will work just fine, but I'm not actually sure whether just C will want to. No, it does not want to do it. So plain C is not smart enough for that. It is nice if you can like write a function with the code that you wanted to do directly here. That is convenient. That is what people want to do. But unfortunately, seems that C is not smart enough for that. So what we will need to do is we will need to outsource the function outside of our main function. We will write our void my list printer. Let's call it. We will give it a this type, and I want to see whether it will accept that as is or it will cast. No, it accepted it. So it only checked whether the parameter count is the same. It did not check whether the parameter type is the same. So that as we have seen here in C, we don't need to typecast between pointers when using C function pointers. It just needs to be a pointer. It doesn't care which pointer it is. It will just accept it, even though we have defined that this thing should have a mylist pointer here. So this again shows how risky just C is. So using C++ is really always the safer option. Even if you are writing just C code, C++ will make it more safe through its much more strict typecasting requirements. So now if you run it, wait, we have a bug somewhere. We forgot the semicolon. Zack. So if we run it, as you see, it printed the values as it did before, just that now it is somewhat more convenient. It would be, of course, most pretty if we could write it like this. Comma, comma. Since it would be C code, it would need the right type. Then it wouldn't work. So C code would be as far more inconvenient as we would need to have a typecast somewhere inside for the thing to work. So for example, we would what's the other type here? Have our entry and then typecast it to entry and then get data1 from it. But as said, this CPP functions which are defined in other functions, often even as arguments to yet another function calls, are referred to as lambda functions. Actually, I don't know why they are called this way. There is some historic reason for that, probably. But it's just important to know that that's how they are called and how they work. And generally, here in this square brackets, you could specify what here of the local variables you would like to capture. So it's called the capture list, and then you could access them from inside here. But obviously, when you think about how that could be conceivably implemented, it becomes immediately apparent that that would not work with just a normal function pointer. So just a normal function pointer is just one number. So if we would want to attach some sort of information, this would mean that our function pointer would have to be a whole struct of containing all references to all these variables or copies of them plus the function pointer. And internally this is implemented this way, but since you kind of cannot define such a function pointer, even not with a type def by hand, this needs a C++ mechanism called templates. The template mechanism allows you to have like a placeholder type, which will then fill in the right type at compile time, and then it can auto-generate this highly complex types that would be needed for a Lambda function for the call to actually work. Presumably, there might be a formal way how you could write down such a type, but this is not something anything would want to do. For now we will, so what you can always of course do is you just use a empty captcha list, at which point this Lambda function defaults to being just a normal function, not in any way different than a function written outside. So inside here, if you have an empty captcha list, you could not refer to anything that's outside. It would be completely isolated. The only advantage of this Lambda function being here instead of being somewhere else is that it's just logically in the place where it's needed to be, while here you always need to scroll to check what this function is doing. So it's a small advantage. And when we later so one homework now, as mentioned, is to make this double linked list. The next homework will be to add a find function. Or need implement the mylist_find function. Right. So that's the first homework. That's the second homework, and at some point, once we have a few lectures after us where we learned what classes are and how they work, and are now settled by then in C++, then the homework will be to port this list to being a C++ sort of list. So instead of having just standalone functions, everything to be contained in one object, and at this opportunity we will be able to also implement it such that we can use templates and with them be able to specify complex Lambda functions for our find function. But now let's specify how this find function is envisioned to work. So we called it mylist_find. Did we? Just to ensure that it's typo free. Yes, it is typo free. find function. So we copy the prototype and we let it return boolean. We'll need to write some more definitions for the whole thing. So wait, what is this complaining about? My find function should not be complaining. My list should be fine. Boolean, it cannot use boolean capital letters. Boolean, now it should not be complaining. Right, good. Right, so let's write a small specification how this function is supposed to work. So mylist_find. And it should return something. It should return the entry. Return the found list entry or null if not found, comma. True. The mylist_find function okay, and now we need to improve this. So first of all we need a void asterisk param. Since we are not able to create full-blown lambda functions with captured arguments and so on. We need some other way to allow us not to have to write a find function each single time we want to use it. So what we do is we provide a parameter which can then be passed to the function. I will demonstrate this with this iterate function later. So we add the param function, and then we could implement also a myListRFind. myListRFind myListRFind operates similar to myListFind. Put it the list in reverse order. The yeah. Okay, so the rfind will be an optional homework. So if you do it, optional. So homework 1, homework 2, and optional. The myList reverse find function. It should be quite trivial for you if you already have done the rfind and made the list being doubly linked. So that's simply the idea is that you can search it from either end, and obviously since we don't have any access to the middle, we cannot do anything to search things in the middle. The list, such a linked list, obviously has this limitation that you have no random access to elements. You cannot access an element by its number. If we would want such a feature, then we would need to create some other sort of list. Or rather, so basically what we would create would either be an array or vector where all the entries are in consecutive memory space, which, as mentioned, has the drawbacks that you cannot easily remove elements in the middle and so on. Or what we could also do to some extent is we could we could go the slow way and just count from either end until an offset, but this gives us the very bad performance, as we have seen. So what we could in principle do is we could have we could allocate an array and basically have the array internally just keep pointers to the individual entries, such that if we have to copy around things because of removing elements, the amount of memory we need to copy is very small, so it would be an improvement in this way. So so we could implement a random access list as one of the later approaches. The main downside to such a list in the context of C development for drivers would be that in such scenarios the list itself needs to allocate and free memory, while in our case here in this simple list it does not. It only changes pointers. So the calling function is responsible for taking care of allocating and freeing memory, which makes our list implementation much more simple. As soon as we start enabling the list to allocate its own memory or deallocate the memory in special scenarios, this will either make our list much more complicated, because then we would need to add, for example, to the structure additional arguments, additional variables containing pointers, for example, to a function that will do a memory allocation, to a function which will do memory deallocation, and so on. We could, of course, rely on malloc and free in user space, and that would be fine. But in kernel, you don't have malloc and free. You have to use the kernel provided memory management functions. So the thing is simply a bit more complicated all in all. So having such a simple list is sometimes really a nice thing. And as I mentioned, we need to pass some additional parameters for the search function. The idea is that you kind of could pass a value for which you are looking for example, or anything else. So we'll add this here, and now if we call it, we need to pass not just the argument but also the param. And as you see, for this part we're already done. We now just need to take a look on our implementation here. So this needs the param. It will not work without it. Oh, I have not activated this. That's annoying. It's the one good feature of Windows 10 that it has a multi-clipboard. Other than that, one could have been stuck with Windows 7 forever. Plus the new hardware support, that's also nice to have. Okay, so we have our param, and now we can more or less select what our param would be, and the simplest thing would be to have a struct as my list printer param. We need to do it again the correct way, or rather the old school way. I would not say that this is any more correct than the other way, it's just the old school way. So we have our param. We need to give it something, so let's say I will give it a string. Some string. Char 100. Okay, and here then we need to cast param to we don't cast, I mean we need it to be cast in the end, but we don't need to cast explicitly since the pointer as a pointer in C++, so we call it printer param. Printer param is equals param. In C that would require a cast, in sorry, in C++ it would require a cast, in C does not. Then we just use here %s comma printer param string. So we just will move a portion of what we want to print into our param structure. So now here we need to allocate it. We'll call it printer param. We can paste it here. We need this to be a reference. We need this to be a pointer. So we need to use the reference operator, and in string we can sprintfs, or just let's be fast, strcpys. This takes in bytes, so see, just size of comma and 3, and then the result will just look the same, just have been obtained a bit more complicated. Just to demonstrate, we just call it here, let's say list entry. Now we will call it list entry, and voila. So for example, if this print function would have it would have different entries, like entries for something and entries for something else, but internally they are the same type, they just have different semantic meaning. So if you want to print them out, then you might want to be able to change how you describe your entries in your enumeration function. Okay, I guess this is a nice verbose example. It should not be too difficult of a homework to do. Yep, so it really is just a bit trickery with adjusting the pointers the right way for everything to work fine. We have our remove function. The remove function does not care. The remove function will be simplified. I should write this down so that no one forgets it. So, whoops, yes. To update my list remove. Entries, okay. Nice. Anything else? Nope. I think this is it within reason. There is nothing else we really would need here. Not for the simple list. if you are interested, let me know. Then maybe later we could implement a list that, or maybe not a list, something more fun, maybe a hash table that would need to manage its own memory, and then I could demonstrate to you how to do that in a way that would be compatible with kernel mode programming. You might have noticed that I'm often referring to kernel mode programming, which is probably something most of you won't do, but it is a good, let's say, good playground for really low-level things. So if you are looking for how to do things, then this is a good keyword to look for when Googling. Also, when you are programming for some Arduino or some other very limited platform, similar constraints like in kernel programming could apply. Realistically, probably your Arduino will implement a malloc and so on as you would expect it in user mode, so that would work just fine if you would have a code that relies on it. But if you want to do things as low level and thus as efficient as possible, you might really want to then have some own memory management, especially given how constrained memory in such a platform might be, and then it would be useful for you to know how you can use a generalized library which then can operate with any sort of memory allocation or deallocation paradigm, and still not require the code itself to be changed. So this is always very good if you write your libraries or your shared code to make it such that when you're using it in another project, you don't need to change it to fit the other project. You can just use it as is. Or if you detect that, oh, you should change something, then you can make the change, and then the thing will still work in all your other projects, so that you really can share the code instead of having a situation where you have like some level of a common library which then have sprouted branches and started diverging, and in the end putting you in a situation where you need to maintain multiple only slightly different versions of the same shared code base. So this usually is a really bad thing, because usually people are not really motivated to maintain such code. You would just always maintain the last version on which you are working, with which you are working, and then if you make some improvements to it or find even bugs in it, you probably would say, well, I use it in the other project, the bug is still there, but the other project didn't crash, so maybe I won't fix that. And obviously if you keep your shared code to be shareable and not specialized for any individual project, then it gives you the advantage that you can easily then have your bugs fixed in even your old projects. You just need to recompile them quickly, and that's that. Since we don't have time to start anything else, I mean, we could go over time if you want, but I realize that some of you might have some time commitment so that you cannot say overtime, hence we will not do overtime, and that should be fine as is. So if you have any questions, let me know. We still have 5 minutes time. For the next lectures, let me see in my short lecture plan what will be the next thing. What I think, so flow control, pointer structures, functions, memory management. Right, strings we had I/O. Well, we had this since writing and printing the console as well. I didn't talk about preprocessor and file I/O, and it would already be it. So in the next lecture, we could actually already start with C++. So be excited for it. It's a lot of fun. It's much more fun than just C. You can do really crazy, enjoyable things with C++. But if you want, we can squeeze a few comments about preprocessor into the last 4 minutes. So let's create a quick project for that. Next, preprocessor. So as the name suggests, it's something that is done before anything else is done. And you have already seen a few preprocessor things. So for example, here this include statement is a preprocessor statement. So before the code actually is compiled, the include statement tells the compiler to take all the data, all the content of the file IOStream and put it here in this place of the file. And as you might remember from the very beginning, I think I showed you also pragma once, which you can use in a header file, so that things which you have included somewhere else will, so that if you include the same header file multiple times, it will not cause the compiler to say that some symbols were already included, but it will intelligently know that the thing was already included. And then to the more interesting things about the preprocessor, so the things that one would really associate with this functionality is the define. Oops, it's not typing. The define is basically a placeholder name, let's say my int, and then you can specify that this is a unsigned int. At this point it kind of behaves like a type diff, but it's not. And the reason is because really it's just a search and replace function. Basically it searches for my int and then replaces it with this. It doesn't really do anything else. So you can also define, or actually let's do my boolean. That's since we have seen that C doesn't have a boolean, it's kind of hacked in by using exactly this mechanism. Let's go my true. Oh, that sounds very politically incorrect. My truth. Truth should be universal. And my false. And now what you can do is you can just use my boolean as a variable name. My boolean. Then initialize it with your very own version of the truth. I mean, we could define it to be 2 actually if we want, but let's stay with 1. Then you can check if my boolean is false, then I don't know, return -1, else return 0 or something. Or we can also print oops, we don't want EOS, we want stdio. Sure you can. Sure you can. It's here already in an if statement. It's already here in an if statement, and it would work just fine in a loop. Well, right. I will make a loop in a second. Oops, I deleted the wrong line. So for, or let's do with while my bool is equals true, then print it's still true. And at some point we should well change it to no longer be true. So let's int counter is equals 0. Next if counter counter plus plus, and if counter plus plus is greater than 10, then it shall be false. My false. Rightio, and now if you run it, it will print true. We forgot the new lines. \n /r/n. I mean, you don't need a \r. Windows nowadays will know what to do just with a \n. Okay, and now we will have this line again. Okay, let's run it. So wait, false. I screwed this up. Oh right, I screwed that up. But this we can fix. True became false. It's still true, and it's true. It's false. It's true. Right, now it should do the right thing. So it's true. It's still true. It's still true until it became false. Alright, and I didn't need to type false again. So this one thing you can use this preprocessor for, and you can do it quite in an elaborate way, because you can even have like a function. Well, it is a function similar thing. You actually saw me doing this here already. Here for this array size. I just make it capital, because usually everything that's a preprocessor should be capital. I mean, should be. It looks nice if it's capitalized, and that's why we should do it. And you can have like multiple arguments and then use them and write a sort of small function, but then just basically the content will be copied everywhere. And since we already are over time, the last thing to show you is that you can use also an if. Let's say if one, else hash elif, and then you can select which code block will be executed. And this either can be like if one, or you could have like if def my boolean. So for example, you could have something like this to give you a real life use case. So if you have my boolean, then you do it, and if you don't have my boolean, then this must be a unsigned char. And what you also could do is you could have like else if. So you can have like else, but the else if is written differently than in normal. In normal C it's hash elif. And instead of if def, what you can do is you can of course have a constant hash if 1 or if 0. This is super useful if you want to enable and disable code blocks, because if you use multi-line comments, the closing multi-line comment would break any multi-line comment that you would try to take around the whole block. So here with this if 0 you can avoid this issue. And what you also can do is you can write if defined my bool, oops. And then what you can do with this if defined, you can and or this with some other conditions. So there is a certain level of complexity that you can use with this preprocessor. We could have like elif defined my other boolean, and then you would hear in this, what was it? Yeah. Then you could have a code like this. So there is a certain flexibility, and it's really nice in a way that you can enable and disable code blocks, make the code blocks change basically their content through this mechanism. What you can do in C++, but not in C, you can refer to other defines inside such a define function, like recursively. Not the sense of a loop, but you can just have inside your array size, you could have another define that gets from somewhere else, and it has a larger level of complexity. With just C, you are usually limited to, you can refer to one define, but you cannot like array size. You can array size 2 from array size x. There are some limits, I don't remember how many, just in C. Just in plain C, so this is something to keep in mind if you get odd errors because of your defines. Check whether you have everything set to C++. Well, and since we are already over time, I think this is a good point to stop. I will upload all 3 projects to Moodle. If you have any questions, you can send them in by mail as well. Yeah, I guess. Yes, of course. Yes. Yes. No. That's the next problem. Define scope. Define is defined until it's undefined. So hash define my def 1, and if, and here my def is still present. If you want to get rid of it, which you might want because it's reasonable, you can use the hash undef and then the define name. Okay, any more questions? Okay, if there are no more questions, then since the last question, I would like to emphasize again that this preprocessor mechanism applies before any code passing happens which would actually understand C++. It is like its very own completely independent programming language. So any structures, any scopes that you might have in C or C++, which can be complex and so on, the preprocessor, it doesn't understand it. It doesn't care for it. For it, it's just a large text file with some special, with a hash defined keywords which have special meaning and are used to just copy and paste text around. That's the whole extent of what the preprocessor does. So that's also why it cannot undefine things when the scope ends, because it doesn't even understand that the function just ended. And you can undefine those things manually. Yeah, well, I guess that's it. We will see each other next week. I think there shouldn't be any holidays, if I recall correctly. Nope. Next week is a normal week, at least according to my calendar. So we'll see each other next week and start with C++, which should be much more enjoyable, I think, and will give you all the power that you always wanted with regard to programming. So, bye bye.